Hey everyone, it's Mrs. Woods. I'm going to be doing a couple of the problems from Thursday night's homework, just to kind of help you with some of the classwork that you're going to have today and tomorrow. So I apologize if the video is a little shaky and if you hear things in the background, it's my kids watching Mickey Mouse Clubhouse. So doing the best we can in this really crazy situation. Okay, so now these problems that I'm working on are from what you were given in class on Thursday for homework that you were supposed to upload yesterday for your classwork grade onto Google Classroom. So I'm going to do number one. So number one is a 1,500 kilogram car initially coasting at 20 meters per second is opposed by an 810 Newton friction force. And we want to know how far will it travel before coming to a stop. So there's a lot of information here in the problem. So the first thing, I have my mass, which we'll get to that in a second, but we're going to focus on the bar chart. So it says the car is initially coasting at 20 meters per second. So that tells me that initially it's in motion. So that's going to tell me that I have some kinetic energy in the beginning. And I'm going to give it 3 bars because we don't want to be, too crazy in the beginning. I'm also going to define my system. So I'm going to have my car in the system, the earth in the system. And now here's where it gets a little tricky because I can see that it's opposed by an 810 Newton friction force. And we know that in our energy and in our bar charts, if we see force, if I see the word force, whether I'm given a force or I'm being asked for a force, if I see force, think work, right? Because work is done by external forces. So I'm going to put the road outside of my system, okay? Because the road is what exerts the friction force. And so it says, how far will it travel before coming to a stop? So that tells me that the road must take away all that initial kinetic energy. Okay, so I'm going to do negative work. We're not going to have any gravitational potential energy because as far as we know, the road is flat. I don't hear anything about springs or rubber bands or anything, so no elastic potential energy. So here we're going to have all the initial kinetic energy being transformed, not transformed, being taken out of the system by work from the road. And I know to put the road outside of the system and have it doing work instead of doing E-dis because I'm given a force and I'm looking for that distance, okay? Which hints to me work, not E-dis. So now that I have this, I'll start with my guess method, givens first. So my given information, I know that the mass of the car is 1,500 kilograms, okay? I know my initial velocity is 20 meters per second. Okay. I know that my friction force is 810 newtons, and that's pretty much all I was given. Then for my unknown, I'm going to put my unknowns over here just because I'm writing kind of big. My unknown is I want to know how far will it travel before coming to a stop. So delta x equals question mark. Okay. So now for my equation, I'm going to go back to my bar chart and I see that I have my initial kinetic energy minus the work done by force friction is going to equal 0. And so then I'll plug in my equation. So I know kinetic energy is 1/2 mv squared. And then I'll do minus the equation for work is going to be the force. And since I know it's force friction, I can actually write force friction times delta x equals 0. So now we can do this 2 ways. We can do it by moving around the variables. So since I want to solve for delta x, I'm going to add this whole term over. So I'm going to do plus the quantity of force friction times delta x, and I'm going to add that over on both sides like that. So then I'll have 1/2 mv squared equals the force friction times delta x, okay? And so then I can divide both sides by force friction because I want delta x by itself. So that'll cancel that. And I'll have force friction on here. So then the equation I'll use will be delta x equals, I can do 1/2 mv squared over the force friction. Okay, so that's my equation part. So then I'll go back over here. Sorry, I'm moving all over the place to do my substitution. So I can do delta X equals 1/2. The mass was 1,500 kilograms. Times my velocity, which was 20 meters per second. And I'll square that. And then divide that by 810 newtons. Okay. And then what I'll get is delta X will equal 1/2 times 1,500 times 20 squared will be 300,000 joules divided by 810 newtons. And for my solution, my last S, I'll get delta X is about 370.37 meters. Okay, so again, started off with my bar chart, wrote down my givens, my equation, and then solved everything. All right, good luck, everybody.